I'm Professor Scott Williams, and I serve as the Managing Director of the Omaha Biofuels Cooperative. The co-op has partnered with Metropolitan Community College to develop biofuels capabilities here in Omaha, to consult on biofuels implementation, and to provide education about biofuels. Today I'm going to be discussing and demonstrating the production of biodiesel from vegetable oil. Even though the reaction has a complicated sounding name, it's fairly easy and straightforward to demonstrate. As you can see here, most of the equipment could be found around the house. The reaction involves three main ingredients, or reactants: vegetable oil, methanol, or methyl alcohol, also known as wood alcohol, sourced from a common gasoline fuel additive, and a catalyst, which is lye, often used in homemade soap making. Both methanol and lye should be used with appropriate precaution, including personal protective equipment. Methanol is volatile, flammable, and toxic with contact on skin. Lye is highly caustic, dissolves many materials, and also produces chemical burns immediately on contact with skin. I'll be wearing a long sleeve lab coat, goggles, and laboratory gloves. The recipe used today will be 200 milliliters of cooking oil, 50 milliliters of methyl alcohol, and 4 grams of the catalyst lye. To start, we need to warm up the cooking oil, which I've already begun here using our modified Mr. Biofuel. Now that the oil is nearly warm enough, we can start with the other reactants. We'll add a weigh boat to the scale and tare or reset the scale to 0, and then weigh out 4 grams of the catalyst lye. Next, we'll measure 50 milliliters of the methyl alcohol into our flask. Next, we'll dissolve the catalyst into the methanol, making a meth oxide solution. The dissolution reaction is exothermic, meaning it produces and gives off heat. At a larger scale, it can even produce dangerously high levels of heat, getting to above the point of boiling for methanol, which is 148 degrees Fahrenheit, significantly lower than the boiling point of water. We're going to use a magnetic stir plate to help provide mixing. In the base is a motor attached to a magnet. The magnet can magnetically couple to a magnetic stir bar, and when the motor rotates, the stir bar rotates, providing mixing. Next, we dissolve the catalyst into the methanol, making a meth oxide solution. It'll take about 3 minutes for all of the lye to dissolve into the methanol, forming the meth oxide solution. Now that the lye is mostly dissolved into the methanol, we can remove the stir bar. We'll measure out 200 milliliters of the heated cooking oil into our reaction vessel. Today we're using a mason jar. We'll place the jar on the mixing plate and add a stir bar. To make the reaction happen, we need heat, which we've provided by adding it to the oil, and mixing, which we get from the magnetic plate, and time. We need to make the reaction happen with heat, but it's critically important to make sure that the temperature is not above the boiling point of the methanol, or else a violent eruption can take place when we mix the reactants. For this, we're using a standard digital kitchen thermometer. As I mentioned previously, the boiling point of the methanol is 148 degrees Fahrenheit. So we just need to stay below that with the cooking oil. Before we react the methoxide with the oil, let's talk briefly about the chemistry that we're going to see taking place. The vegetable oil and methyl alcohol are going to undergo a reaction called transesterification. It sounds complicated, but the name's fairly straightforward. Trans means cross. Ester is the name of a specific type of chemical bond in the vegetable oil, and ification is the process of making. So transesterification is the process of crossing and making ester bonds. The vegetable oil and the methyl alcohol will cross-cut each other's chemical bonds and form new chemical bonds. We'll be left with biodiesel, technically called fatty acid methyl esters, FAME biodiesel, and glycerol, which is also known as glycerin. Glycerol is water soluble, but isn't soluble in the oily biodiesel, so it'll fall down to the bottom. The two phases can't mix, like oil and water, so they separate. Here's where the really good stuff happens. We'll mix the methoxide solution in the heated cooking oil and watch the reaction happen. Initially, we can see the amber-colored oil getting lighter as we mix in a colorless liquid. As the reaction takes place, the glycerol that has been cut away from the vegetable oil will start to appear. Glycerol from used cooking oil is significantly darker than the vegetable oil, and it'll make the entire mixture start to appear dark. Now that we've given enough heat, mixing, and time for the reaction to take place, we'll stop the mixing. We need to let the glycerol settle down to the bottom. Glycerol has had time to separate and settle out of the biodiesel, leaving two distinct layers clearly visible. In about 24 hours settling time, the biodiesel would appear completely clear and all of the glycerol would be down at the bottom. With a valve at the bottom of the container, we can drain away the glycerol and leaving just the free biodiesel on the top. The byproduct glycerol can be useful in the process of making soaps. The last step would be to wash away any residual reactants or contaminants in the biodiesel, such as soap. Then the final fuel is ready to use. Biodiesel is a drop-in replacement for petroleum diesel in any diesel engine application. Cars, vans, trucks, trams, trains, semi-trucks, generators, even heating applications. Biodiesel burns cleaner at the tailpipe, emitting less soot and less air pollutants. With no sulfur in the fuel, there's no sulfur oxides released from the tailpipe, which can contribute to smog and acid rain. Since biodiesel is produced from biosources, it's a net zero carbon cycle, and there are no contributions of CO2 as a greenhouse gas that can cause global climate change. Biodiesel can be made from recycled sources, including used cooking oil, and can be produced domestically, even locally, right where it's needed and used. Stay in touch with Metropolitan Community College and the Omaha Biofuels Cooperative to keep learning more.